Generative models and their applications. A generative model is a type of machine learning model that learns the patterns in a set of data so that it can create new data that looks similar. These models play an important role in AI because they try to understand how the data is formed. To understand this better, imagine teaching a child to draw animals. You show the child many pictures of different animals. After observing them, the child starts to recognize common features, like ears, tails, or body shapes. After some practice, the child may draw a new animal they have never seen before by combining what they learned. A generative model works in the same way. It studies many examples and then creates something new that follows the same patterns. Generative models work by identifying patterns and distributions in their training data and then applying those findings to the generation of new data based on user inputs. The training process teaches the model to recognize the joint probability distributions of features in the training dataset. Then, the model draws on what it has learned to create new data samples that are similar to its training data. Generative models are typically trained with unsupervised learning techniques, when they are fed a mass of unlabeled data and sort through it by themselves. The models figure out the distribution of the data, which is how they cultivate the internal logic they then use to create new data. During training, the model applies a loss function to measure the gap between real-world outcomes and the model's predictions. The goal of training is to minimize the loss function, bringing generated outputs as close to reality as possible. Generation of new content is a probabilistic process. Generative models do not know things in the same way that humans do. Rather, a generative model uses complicated mathematical equations to predict the most likely output based on the rules it learned during training. In machine learning, it is important to know the difference between generative and discriminative models. Generative models try to learn how the data is created. For example, if generative models are trained on pictures of cats and dogs, they learn what features make a cat and what features make a dog a dog. After learning this, they can generate new images that look like cats or dogs. Discriminative models do not try to create new data. Instead, they learn how to distinguish between categories or labels. Using the same example, a discriminative model learns to recognize whether a picture is a cat or a dog, but it cannot generate new pictures of animals. Many types of generative models exist, each with its own defining architecture. Deep generative models are a subtype of generative models that use multi-layered deep learning neural network structures to understand complicated, multifaceted relationships between data points in a dataset. Now let us briefly discuss the major generative models and their applications. First, let us discuss the autoregressive models and their applications. Autoregressive models predict the next item in a sequence based on prior items. They assess the components in the sequence to determine the probabilistic correlation between them, then use that information to identify a new component that would likely follow. Autoregression is a type of linear regression, which is a statistical technique that predicts the value of a variable based on the values of one or more variables. Autoregression narrows the focus to the target variable but considers its values over time. Autoregressive models take the form of recurrent neural networks, RNNs, or transformer architectures. Autoregressive models, especially transformers, are in widespread use today. Many of the leading generative AI models are transformers, including OpenAI's GPT and GPT-4o, Anthropic's Claude, Meta's Llama, Google's Gemini, and IBM's Granite. The major applications of the autoregressive model include 1. Natural language processing. Transformers can process complex natural language queries and respond conversationally with automated text generation, making them ideal for use as chatbots. For example, ChatGPT is OpenAI's chatbot implementation of their GPT generative model. Other NLP applications include sentiment analysis, speech recognition, text-to-speech, TTS, applications, and document summarization. 2. Coding support. The same autoregressive capabilities that enable transformers to excel at text generation also allow them to debug code and generate code snippets. 3. Time series forecasting. Autoregression can be easily applied to time series forecasting, in which a model predicts future values based on previous trends. Time series forecasting is frequently applied to financial modeling, market predictions, and weather forecasting. 4. Reinforcement learning. Transformers have begun to see use in reinforcement learning, a machine learning training technique that teaches autonomous decision-making. Transformers are also being applied to classification tasks. Now let us discuss the second generative model, that is, the diffusion models and their applications. Diffusion models create new data by gradually adding noise to a dataset, then figuring out how to remove the noise and yield novel output. Diffusion models gradually obfuscate or diffuse input data by adding noise, then refine the mess they created into new, similar data. They generate new data by learning to refine noise into data that is similar to their training datasets. Diffusion models work through a three-stage process. Step 1. Diffusion. During training, the model gradually introduces noise to its input data until the data is no longer recognizable. The model adds a small amount of Gaussian noise to the data at each step in a mathematical process known as a Markov chain. Step 2. Learning. The model traces the evolution of the now destroyed data to understand how it was altered through the noising process. Diffusion models repeat this process at each stage of noising. Step 3. Reverse diffusion. By understanding how noise alters data, the diffusion model learns to reverse the noising process and reconstruct the input data. The goal of reverse diffusion is to travel backward through the Markov chain, removing Gaussian noise until only the pure data is left. Steps 1 and 2 are applied to train diffusion models. After training, diffusion models generate data by reverse diffusing random noise to find the data requested by the user's prompt. Diffusion model applications include 1. Image generation. Diffusion models power mainstream image generation and image synthesis tools such as Midjourney, Stable Diffusion, and OpenAI's DALL-E 2. These models generate images in response to user prompts. Diffusion models can generate high-quality realistic images, including those of human faces. 2. In-painting and out-painting. In-painting is the process of adding or removing content within an image, while out-painting expands an image beyond its original borders. 3. 3D modeling. Google's Dream Fusion and NVIDIA's Magic 3D are diffusion models that create 3D models from text inputs. 4. Market research. Diffusion models show how things evolve over time, making them useful for understanding how consumers react to a product. 5. Anomaly detection. Because they can learn how data changes over time, diffusion models can identify when data points do not fit established trends. Anomaly detection applications include cybersecurity, fraud prevention, and disease detection. Now let us move on to the third generative model, that is, the generative adversarial networks and their applications. Generative adversarial networks, GANs, pair a discriminative and generative model together in a competition, with the goal being for the generator to create output that fools the discriminator. The generative model creates outputs that a discriminator model must reason authentic or fake. The objective of the competition is for the generator to generate content that passes for authenticity when judged by the discriminator. Both networks in a GAN are often convolutional neural networks, CNNs. GANs are used primarily in the field of computer vision and other graphics-related tasks, such as 1. Computer vision. Computer vision is the use of machine learning to process information from images. Common computer vision tasks include object detection and classification, facial recognition, sign language translation, and object tracking. 2. Image generation. GANs can outperform diffusion models in the generation of realistic images. They also require less training time and are more compute efficient, though diffusion models offer finer control, greater versatility, and more stability. The diffusion GAN framework trains a GAN with diffusion to maximize the benefits of both model types. The applications of GANs include 1. Anomaly detection. When trained to generate normal datasets, GANs can be applied to anomaly detection tasks. The GAN creates a synthetic dataset modeled on the real-world data, and by comparing the two, anomalies in the latter stand out. The discriminator can also detect anomalies by declaring certain data points more likely to be fake. 2. Data augmentation. Data augmentation, the use of pre-existing data to create more data samples, can boost computer vision performance even further with CNNs. This process differs from synthetic data in that it expands on real data, as opposed to generating something from scratch. Now let us briefly discuss the next generative model, that is, the variational autoencoders and their applications. Variational autoencoders, VAEs, compress input data with an encoder, then reverse the process with a decoder to create new similar data. VAEs learn the distribution of a training dataset and apply those expectations when generating new data from encoded samples. Like all autoencoders, VAEs comprise two components, an encoder and a decoder. The encoder's job is to learn the latent variables in a dataset. Latent variables are not directly observable but play a significant role in data distribution. Latent space is the collective name for all the latent variables in a dataset. The encoder models the latent space in a way that captures the information needed to accurately reconstruct the data. All other variables are omitted. The decoder takes the compressed representation of the data and extrapolates it back to the data's original form. An effective decoder produces output similar to the original pre-compressed data. VAEs excel in areas like 1. Image generation. VAEs see use in image generation, though with mainstream image generation applications, diffusion models have widely replaced them. Compared to other image generators, VAEs tend to produce blurrier images due to their averaging of the latent space. 2. Genomics. VAEs aid geneticists in calculating breeding values, the projected value an animal will provide with its offspring, as well as assigning disease risk scores. 3. Anomaly detection. VAEs are cheaper and easier to train than both GANs and diffusers, making them an attractive choice for anomaly detection tasks. The recreated data is compared to the original data to isolate instances that deviate from the projected distribution. 4. Data imputation. VAEs can generate new data to replace missing data and restore corrupted files. Examples include clearing up audio files and denoising videos as well as medical imaging. While VAEs tend to generate blurry images from scratch, they can restore pre-existing blurry images by denoising the image. 5. Semi-supervised learning. VAEs help train classifiers by capturing data distributions in datasets with incomplete labeling. VAEs can also perform data augmentation to generate extra training samples for the classifier. Finally, let us discuss the flow-based models and their applications. Flow-based models utilize a series of invertible mathematical transformations to map a simple probability distribution to a complex data distribution, that is, flow-based models learn the relationships between simple and complex distributions of data through reversible mathematical operations or transformations. Data can losslessly progress through this pipeline, known as a normalizing flow, in either direction. While VAEs and GANs estimate data distributions, flow-based models explicitly learn the probability density function for the dataset. In a given dataset, the probability density function describes how the data is distributed. Normalizing flows progress from simple distributions to complex ones until the target variable's probability density function is identified. Flow-based models can generate new data samples that maintain the same statistical properties of the initial dataset. Like all generative modeling, the process is based on the concept of drawing samples from training data and applying complex statistical mathematics to produce similar, novel outcomes. Applications of flow-based models include 1. Image generation. Flow-based models generate images by running randomly sampled noise through normalization flows to produce a clean image. Pixel CNN is a notable image generation model that applies autoregression to the sequence of transformations, modeling images pixel by pixel. 2. Accurate density estimation. Density estimation is the challenge of identifying the probability density function of a dataset based on observable data. While flow-based models can accurately represent complex data distributions, they struggle to capture long-range dependencies when compared to transformers. 3. Molecular graph generation. Flow-based models have found use in molecular graph generation, in which new molecular structures are modeled as graphs by generative AI models. Molecular graph generation is an important tool in aiding scientists and engineers in the discovery of new drugs and materials. Thank you for watching this video on scope of generative models and their applications. In the next video of the Generative AI series, we will explore the topic, Importance of Generative AI in Various Domains. Do watch it to continue your learning.